Hello everyone and welcome back to Math Made Easy. In the previous lecture, we completed the chapter on error analysis, where we learned how to measure and interpret errors in numerical computations. Beginning with today's lecture, we enter one of the most important areas of numerical analysis, the solution of nonlinear equations. So before we learn numerical methods such as the Bisection Method or the Newton-Raphson Method or more, we first need to understand the type of equations these methods solve and the mathematical theorem that guarantees the existence of a solution. And that theorem is known as the Intermediate Value Theorem, or you can simply state it as IVT. Now the question is, what do we usually mean when we say solve an equation? For example, if I write this x plus 5 equals to 9, we get x equals to 4. That means solving an equation means finding the value of the unknown variable that satisfies the equation. And there are two types as of the linear and the nonlinear equations. What if I write this 2x plus 3 equals to 7? We get x equals to 2, where the variable is having the power 1 and the graph is usually a straight line, and this usually solved exactly. Now if I write something like x square minus 4 equals to 0, or e to the power x minus x equals to 0, or sin x equals to x minus 1, or x cube minus x minus 2 equals to 0. So these equations actually involves powers greater than 1, exponential functions, even the logarithmic function or the trigonometric functions, and many nonlinear equations can be solved exactly. And that is where the numerical analysis becomes essential. Now the question arises here, what does that root actually means? So a value of x that satisfies the f of x equals to 0 is called a root, a zero, or a solution of the equation. For example, if I write x square minus 9 equals to 0, I'm getting the factors as x minus 3 and x plus 3 equals to 0. Then we get the roots as x equals to 3 and x equals to minus 3. And when an equation is written in the standard form fx equals to 0, we get the root, 0, solution. These all three terms refer to the same values of x. However, in a broader mathematics, solution applies to any equation or any inequality or even a system. But a root is generally reserved for the equation of the form fx equals to 0. And the 0 emphasizes the function's output must be 0. Now, some equations can be solved using algebra, but what about equations like e to the power minus x equals to x? Can we isolate x using elementary algebra? It's clearly no. And that is why these equations require numerical methods. Now if I draw a curve that crosses the x-axis, notice that wherever the graph intersects the x-axis, this fx equals to 0. Therefore, the x-coordinate of that point is actually known as to the root. So before searching for a root, we need to know whether a root actually exists or no. And that is precisely what the Intermediate Value Theorem tells us. So letting this fx be a continuous function on the closed interval a comma b, and if this f of a and this f of b is lesser than 0, then there exists at least one number c in the closed interval a comma b such that this f of c becomes 0. Now if I say the function is continuous, that means the graph has no break. And the closed interval I'm taking it as to be 1, 4. Now if I'm getting the f of 1 is greater than 0 and f of 4 is also greater than 0, then there doesn't exist any C that belongs to closed interval 1, 4 such that f of C becomes 0, because the graph is not cutting the x-axis in this interval, and that represents that there doesn't exist any root. And because the function is continuous, it can't jump from a positive value to a negative value without passing through 0. And that is the central idea behind this IVT. Now if I take this fx equals to x cube minus x minus 2 in the closed interval 1, 2, and I'm getting this f1 equals to minus 2 and f2 equals to 4. And since the product of these two functions is actually, I'm getting it as lesser than 0 because of the opposite sign. That means there exists at least one root between 1 and 2. And since we haven't found yet the root, but we have only proved this root exists in the interval. Even the bracketing methods that begins with the Intermediate Value Theorem. Even the first method that we are going to study, the next Bisection Method, that repeatedly halves an interval that satisfies the IVT theorem until the root is located with the desired accuracy. And without this IVT, the Bisection Method has no mathematical guarantee. So today we established the mathematical foundation for solving nonlinear equations by understanding the intermediate value theorem. Now we know how to determine whether root exists within a given interval or no, but we still need a systematic way to approximate its value. So in the next lecture, we will begin our first root finding algorithm, the bisection method. We'll study its principle, derive its algorithm step by step, and understand why it is one of the most reliable numerical methods for locating the roots of continuous functions. So if you found this lecture useful, continue with the next video in the playlist so you don't miss the flow of the course. Thank you for learning with Math Made Easy. Until next time, keep learning, keep questioning, and keep exploring mathematics. Thank you for watching, and I'll see you in the next lecture.